Good morning. Happy Bowtie Friday. This ETH.BUILD is focusing on blockchain. Really cool thing. I'm wearing this clown bow tie or Bitcoin bow tie for it. Here we go. So, in the curriculum so far, we've jammed through key pairs and hashes and ledgers. And what we found is if we want to transact value back and forth on a distributed network, not a centralized one, we end up having problems of coordination. We end up having this issue where we can't find a consensus between disparate parties because they all receive different transactions at different times. And there was a lot of different ways to solve this, but none of them were great until proof of work came along. And we dove into the Byzantine generals as a side quest, but what we learned there is basically the generals needed to prove they had an army when they sent messages over an insecure network. So then when they were received, the receiving party could tell that that person was indeed a general with an army that was going to attack, and then they could coordinate. So with this ledger, we are pumping in transactions from the network, and these are just random, it's just simulated transactions. But we'd rather not Eve have to have an entire army behind her to be able to send a transaction. So we're going to abstract away the proof of work, the work that you have to do, into a block of transactions and let a miner work on that. So what we do is we bring in a block, and this is just going to hold the transactions, whatever's coming across the network. Okay? Oh man. So whatever comes across the network, we're going to load up into this block. And then if we were to look at the structure of this block, it also has a nonce. Okay? And what that nonce does is it lets us tweak this hash. So what we're doing, if I were to take this entire block and stringify it and hash it, I would get this hash up above. And we'll see that as transactions change, that hash changes. But also, as I type in this nonce, that string is also going to change. So I'm doing some work here. I've got a random set of transactions, I'm doing some work, and boom, look at that. Okay, so this nonce happens to hash with all the transactions and give us this leading zero. And if you watch the side quest about the Byzantine generals, we kind of just pick this leading zero as this arbitrary amount of work. So let's just jump back just a tiny bit and look at what's going on here. So if I turn this into JSON and then I hash it, oh, it's not going to work. I need to remove the hash. One other thing, this. So if I take this mined block and I pull out the hash and I JSON encode it and I drop it into a hash, I'm going to get, cool, a leading zero there, right? I can prove that this block has been worked on. Okay? So what the difference here is, what we're talking about here is this work, right? So I was talking about adding a counter and having that counter go into a hash, and then you would just kind of like, you have to do some work, right? Like the hash function costs work. It costs CPU, right? Which is technically a limiting resource here. So we're putting out all of our CPU, trying to jam on this string, trying to find this leading zero. Okay? And once we do, we have a valid block. The block is basically frozen. Whatever transactions were here at the time are in this block now, and sort of everyone respects it, and we can move on to the next block, right? So a new block comes onto the network, but watch this. Here's the trick. We take the old block and we wire it up to the new block. So now if we look at the structure of this thing, it has no transactions, an empty nonce, but it has a parent with transactions, right? So the previous block's hash is going to be part of the next block. So we'll have like a whole chain, okay? So let's throw in whatever the latest transactions are out in the pool of transactions of people that are wishing to send stuff on chain, right? And then let's work on finding a nonce. This time I'm going to do that whole counter thing. I like that better. Feels like a clicker game. Okay, so boom, boom. Now I'm just going to kind of increment this nonce, jam on it until bam, I find, check that out. Block number 2 is mined. Look, I needed a nonce of 10 to make these transactions valid. Awesome. Okay, so I can unhook that. We can kind of minimize this guy down. And now we're looking at block 2. Okay, so this is too easy, right? Basically, I'm able to find a valid block very quickly, and what you want is for that to be harder. So I'm gonna turn the difficulty up to 2. We're gonna wire this one up, so he's gonna be block 3. We're gonna bring in the latest transactions, and then I'm gonna have this counter run, but I'm going to set it up on like a timer, so it just kind of jams away. Okay, and let's maybe speed that up to, you know, four times a second or so. Okay, so it's just clicking away, trying to find a nonce. We're basically mining away at this, right? We're using our limited CPU power to just like arbitrarily throw random hashes at this until we find a hash that has the leading 0. And this time we need 2 leading zeros because our difficulty has been turned up. All right, that's going to take a bit, right? So what we can do is I want to basically bring in a miner and do this a little bit faster. I was hoping this guy would find one with a leading 0. Can we see the hashes? Yeah, so we're waiting for 2 leading zeros, and that might take a little bit. So I'm going to replace this counter with... Oh, he found it. He found it. Okay, good job. Good job, counter. Good job. Okay, so block 2 we can minimize. Block 3 is now valid. We can unhook the transactions. All right, let's start another block off of this one. Okay. And even though it has transactions in it, it'll clear in a second when I get that. But this time I'm going to hook a miner up too. I want this thing to really do some work. And if we want to see what a miner is, let me just jump just real quick over to the Byzantine's general and load that up. What we found was this general who wanted to attack at dawn needed to have all these soldiers in order to be able to attack. And what's going on inside of that soldier is exactly what we're doing here with our miner. We're taking his message to attack at dawn and some nonce, and we're working on it. We're basically throwing it in this hash function as fast as we can, trying to get those leading zeros. And the leading zeros are just some arbitrary thing we've all agreed on, that like this is enough work to prove that you are a soldier or you can wage war. So what I'm going to do is just kind of take that soldier and I'm going to bring it into the latest ETH build as just a miner. And that miner is going to do that exact same thing. So we're going to have transactions that are coming in from the pool. We're going to then pump those into the block. There we go. And then the miner is just going to work on this until he finds... There we go. So now the miner is just chugging along. Very similar to our counter, but he's kind of doing things in the background, kind of working on it. He's not like updating all this stuff, and it's more efficient. Like he's more focused on mining, and it's not... Okay, so just a counter randomly. Okay, so here we go. Let's... I mean, he's just randomly throwing hashes. I guess that's exactly what our miner was doing. There's no smart way to mine, right? It's all an efficiency game. You're just like chugging away at hashes, right? You want to have cheap electricity. There's stuff... I don't know anything about mining. Not a genius. But he's just jamming away, and what I can do is speed him up. So if I speed this up, we're going to hopefully quickly get to a mined block here. Come on, miner! So, now, what's going on across the network? If I were to draw this, so we've got these miners, right? And they're all over the network, kind of spread out. Hey, he mined a block. Good job. And then we also have just these users, right? That are also talking to the network. They may be running a full node, they may be not, but they're not mining. They're just wanting to send some transactions. Okay, so that's our topology. Very distributed. There's no central figure. Okay, so let's see. Let's minimize 3. Let's bring 4 down here. All right, let's make this even harder, right? A difficulty of 2, this miner was able to find pretty quickly. What you want is for the entire network to be working and only one guy within that network to find it within some certain time period, right? So we'll wire up this guy as the parent. So now we're on to block 5, and we'll say the difficulty is now 3. All right, and I think we need to change our miner's difficulty too. Yep. Okay, so now he's chugging away, trying to find, and we'll wire that block back there. There we go. Okay, so now we've got this guy trying to mine this block. Now, we talked about this issue of double spend, or even this issue of like network propagation. When we have a ledger and we have a distributed network and someone sends a transaction over here, it gets to different people at different times, and therefore we end up having a consensus problem because we're not sure of the ordering of things. And that's why we're doing all this mining. Look at that, he's already found a block. Good work, miner. So there's also an issue here where these blocks eventually, we're going to have someone mine what is called an uncle. And let's just set that up here. So let's see, unhook this guy, let's bring in another block. Here, do it here. Come on, Griffith, you've used this before. Okay, so let's hook up this guy as the parent, and we can disconnect him. Okay, so we've got this miner that will be working on transactions. But what I want to do is bring in a second miner. Okay? And let's go ahead and give these guys names. So let's see, miner M Mallory. Mallory is usually the attack account, but we'll have Mallory the miner over here. And Mike, both mining along. Okay, so now we need to run this over. Oh wait, something's not right. We mined a block with a 0. Something's not right there. Let's get rid of this. Okay, I think our difficulty wasn't there, and the miner was like, oh, I got block 6 right here, and he would have put that across the network, and the network wouldn't have respected it, right? Like so everybody's working on the same rule set. I'm just kind of changing it around willy-nilly over here, but that's something that is like a slow governance thing on chain. So let's see, difficulty, not on chain, but voted on by the miners, basically following the chain. We'll dive into that. So the difficulty is 3. Okay, we're good to go here. So then let me grab this block and move it over here. What I want is 2 different miners to be working on the same problem, kind of listening to the same transaction pool, and coming up with different nonces, hoping to mine the block. Okay, there we go. So I think he's working on that one. Let's actually slow it down for a second, so they kind of work on it together. And then we'll run that back to there. Okay, I believe, yes. So Mike and Mallory are both, we've got 1, 2, 3, 4, 5 blocks. Then the 6th block is still up to be mined. It's up to the network. We've got transactions going across the network, people who want to exchange value, but we haven't mined that block. We haven't found those leading zeros. So let me just put this on fast forward. We'll see the miners really jamming on that. So the next issue with the network propagation is this. So block 5 is block 6's parent, right? There's like this. Whenever you do a blockchain talk, you have to make sure you draw the arrows going backwards, right? So that's my parent, right? This is what a blockchain looks like. There's like a pointer back to the previous block, and you're using the hash from that previous block in your next block, okay? So my arrows, well, that's a bad drawing. But what can happen is you can get 2 block 6s here, and that's what we're gonna run into here. Is 2 different miners come up with a valid result at the same time. So let's say this miner here is going to come up with that result, and this miner here is going to come up with that result. And it's going to move across the network, right? At different speeds. So this guy, right? Are we seeing what's happening here? So if you're this purple guy right here, you think that this is the main block. Oh, let's get the color right. You think that this is the main block because it's the first one you saw, and then later on, this one came to you, right? So you're sort of keeping the mine chain, and then you have this choice of whether to fork off. Fork off, buddy. And then you've got this guy over here, the blue guy, who's sending out also a valid mined block, number 6. Well, we got 2 zeros there. I feel like something's not right here. Difficulty is 3. Is difficulty 3 here? I mean, we should have... This guy should have found a mined block already. Maybe not. Okay, so so if you were this purple guy over here, you're going to see the blue block as yours. So what happens is there's going to be this sort of fork in the network. And we're not going to be sure who to follow, right? So if Mike mines the block, of course Mike wants to continue on. And here's why. We get into the crypto economics of it. What we're going to do is we're going to also set this up to this block up to oh man, this is hard to see. Let me here we go. We're going to set this block up to require that a miner is added in, and then we're going to set the miner to add itself to the block. Okay, so what it's going to do is when it mines the block, it says here's all the transactions we want. Here's the parent, right? We're also going to say here's the person that mined that block, and it's called a Coinbase, I think, but that's like a company now, and it's different. So we're just going to call it miner. So our blocks are now requiring. Man, you would think one of these guys would have mined this block. And that maybe 3 difficulty is right where we need to be. Oh, there we go. Look at that. Okay, so Mike just found the block. But look at this. So Mike is also going to get a value of 10 out of this. So we need to incentivize the miners to do all this work, right? They're spending money to buy these rigs to basically make the network secure. Oh, look at that. Perfect timing. Look at this all coming together. So these miners are spending money to secure the network. And they're securing the network with all their hash power, right? With all the miners combined, tens of thousands, maybe? I don't know. You'd have to look at network stats. But there's these miners that are paying good money to build these rigs that are working on these hashes. And to incentivize them, we give them a cut called the block reward of each block that they mine. So in this version of the block, Mallory has $10. But in this version, Mike has $10. So each of these 2 players are incentivized to keep going down their own chain, and the rest of the network needs to find a consensus. And basically, it's who has the longest valid chain. So what's going to happen is Mike is going to go down this way, and he's going to set up that one as the parent. And he's going to move his miner over, and he's going to start working on this next block, right? And Mallory is going to do the same thing, and it comes down to who else on the network picks whose side. And since we don't want to sort of punish people with bad networks, I'm pretty sure that both of these blocks would get paid in Ethereum. I'm pretty sure that we pay Uncle blocks because they're helping to secure the network. But anyways, you get that. We had this problem of coordination and consensus, and we solve it by putting this arbitrary amount of work that has to be involved to make transactions valid. So Mallory did all this work, hashing and hashing and hashing, to find 3 leading zeros of a hash that is of all these transactions and the previous block, right? So then we have this chain. And what we can do now is we can add, oh man, Hacky React, ready? 1, 2, 3, 4, go! Yes. Okay, we can add blockchain on top. And Hacky, it's all my Hacky code, by the way. So no one to blame but myself. So we can talk to whatever the longest chain is. So Mike hasn't gone to 7 yet, so we can see that the height is still 6 over here. And we can do things like query for balances from people. So it looks like Heidi just got. Let's see what Heidi's. Let's go with Ivan. Here we go, and we hit balance, and what do we get? 524. So Ivan's sitting on 524, or whatever the native token is for this chain. And okay, and we can see his nonce. We can do everything that we could do with the ledger, but now we're kind of stacking blocks, and those blocks are. Holding transactions, and we've abstracted away the work from the users who are just sending money to miners, and we've incentivized them by giving them this block reward. That reminds me, there's also going to be a small amount that each person pays per transaction, but we'll get to that in a later episode. We don't want to talk about gas right now, but it kind of helps to know that there's an incentive not just to mine a block, but to mine a full block with lots of transactions, but it's a smaller incentive, so we'll get to that eventually. Okay, last piece here is that as the blocks are mined, they become more and more secure. And let me show you what I mean by that. Has oh yeah, look at that. So Mike mined a block. Mallory was over here doing a demonstration, and so she was not able to mine a block. So now Mike is that's going to be the longest, and it'll go across the network. Everyone will see it and be like, okay, this chain has 7 blocks. They're all valid. This is the one we're going to follow, right? And you can get hard forks, contentious forks, where actually the algorithm of consensus, like the rules that we're playing by, are going to change, and different groups of humans want to follow the different chains. Cool stuff. Okay, finally, let's if we go back to block 3, okay, and we change something. If we change any little detail of anything here, I'm just going to get in. It's going to be hard to do, but I'm going to get in here. Oh man, this is really hard to see, but here we go. I'm at this text box, and there's some transaction to Frank here. Oh, it's from Frank to Frank. That's not going to work very well. Okay, well, we'll just change it. We'll say that's from Eve now instead of Frank. Now, watch what happens when I hit OK here. Look at that. I changed a tiny little piece of block 3, and all of a sudden the entire chain falls apart, right? It's no longer valid. If I were to broadcast that over the network, people would laugh me out of the house, right? So you can't change anything once a block is mined unless you go back and like remine the stuff as it changes, right? So like I would basically have to hook the miner back up here and try to have enough power to catch up to Mike all the way here with 7 blocks. So it would be very, very hard. The deeper it is, the more, like, the harder it is to come back from. So the fact that this block 3 here, and Carlos sent 84 to Bob can be pretty secure, knowing that like multiple blocks deep, like that money's there for sure. There's no way that there's going to be some contentious fork here. Like, I'm solid. So that's I think that's where we call it finality. But there's more stuff that gets into that. It's over my head. I'm still learning, but. Blockchain. There we go. So instead of having a ledger and having this consensus issue, we use proof of work to jam on a hash to validate a block, and valid means arbitrary zeros. And we're still going to run into issues as we build that chain of blocks up with network issues, right? Where mined blocks can actually get to different places at different times. So we have to have a further consensus algorithm that says follow the longest chain that's valid. And that follows the rule set that you wish to participate in, right? Awesome. All right. Happy Bow Tie Friday. That was blockchain on ETH.BUILD. I will save this and put it up there so you can just hit load and have a chain to play with. Cool. Thank you. Happy Friday. Woo!